So my name is Eugen Geylik. I live in Montreal in Canada, and I work for the company which is called Predict AOG. So I just wanted to thank everybody for, the organizers of the symposium for a great symposium. It's very well organized. I've seen a lot of great technology being presented, but my presentation is about old technology which was built in 60s, last century, and first was flown on Boeing 747 Classic in 1968. So next slide, please. So the presentation is premised on historical data analysis. It covers the operational impact caused by aircraft-related AOG events and recommends solutions to predict and prevent AOG through systemic maintenance and use of alternative replacement parts to minimize component maintenance cost. So we're using 767 pneumatic system as a case study, as an example. We'll discuss the areas of operation, maintenance, and design, which is operational impact on flight schedule, troubleshooting issues caused by system design complexity and solution, component issues and solutions, changes to aircraft schedule maintenance program, flight crew reporting difficulties and solutions, and plus impact on inventory management. Next slide, please. So learning points are failure predictability methods, failure prevention process, flight crew defect reporting, which is specific to 767 pneumatic system, operational maintenance, cost avoidance, and resultant economic benefits. Next slide, please. So here's the challenges with the pneumatic system operation. First, it goes back to the design architecture, which is complex, and accessibility to the system components, system indication complexity, and in several cases, ambiguity of system indication, flight crew reporting inconsistencies, lack of scheduled maintenance program, which means that most of the system components are flight to failure. There is no preemptive removals of components for restoration. Inconsistent component maintenance, high failure rates, high failure repeat rates, heavy dispatch restrictions. And despite of decades of efforts to improve system behavior, it's still on the top of flight schedule disruption offenders. And all of the above results in operational and maintenance cost impact, which is broken down into 4 items below, which is considerable flight schedule impact, delays, cancellations, which leads to loss of revenue for the operators, excessive maintenance costs, primarily for components. So the excessive cost is about 50%. High rate of unjustified component removals, which is also about 50%. And the result is prolonged aircraft out of service downtime. Next slide, please. Here is the very generic schematic, and the system we're talking about is highlighted, that's circled in red at the bottom. So that's the overhead panel. The pilot's overhead panel is how it looks like. Next slide, please. Here is like a block schematic of the pneumatic system, and you can tell that it's not a simple system. So I'm showing here the left engine side, and it's made of components shown on the screen. Starts with the high pressure control, then pressure drops to certain, like to 97 psi at PRE stage, and it goes to temperature control, and then it and finally it's controlled by PRSOE and goes into system distribution. This is very, very generic, and it doesn't represent the whole system, which includes about 60 line replaceable units total on both sides, approximately 60, maybe more. Next slide, please. So here is the design architecture, indication, troubleshooting the system. Each site includes several subsystems, like shown before: HPSOV, PRV, temp control, and PRSOV. These are the primary components, just the primary components. There's a lot more, which trigger indication in the cockpit and air supply bike module. Failure of any system element renders the entire system inoperative, which creates a heavy impact on operation. Most of the system elements are located in hot and high vibration environment, and it's pretty time consuming to access most of the system components, which are located underneath the engine cowls. So the access is gained by opening engine cowls, or PRSOVs installed in a very small niche in the pylon. So it's very difficult to access, and it takes a lot of time to replace it. So basically, what I'm trying to say is that rectification of failures takes sometimes very long time, and aircraft grounded. System flight deck effect logic is very intricate. It is comprised of ICAS messages, overhead panel annunciator lights, as well as engine and duct pressure parameter combinations. Most of the indication combinations indicate more than one system failure mode. So as an example, if ICAS displays engine HPSOV message and bleed light, which is shown here, you can see the bleed light on the left side on the overhead panel, and all of these ICAS messages. Then it may represent several failure modes. Just basically one message represents several modes, which requires troubleshooting efforts to actually isolate the one within this four that I specified below. So it can be the valve itself, which is high pressure shadow valve, high pressure controller, wiring, sense, servo pressure lines, and bleed air control card. So this is the primary elements that need to be troubleshot. So system troubleshooting is difficult. Isolation of a system failure mode may take several hours and numerous attempts, which leads to flight delays and cancellations, and certainly increase in operations and maintenance costs. Next slide, please. So the economic impact I just mentioned before. So flight schedule disruptions and resultant revenue loss, exorbitant maintenance cost, which is primarily driven by component maintenance. Unjustifiably removed components require recertification. So even if components don't fail, you still have to pay to recertify them. And certain CMM test limits are excessively tight. What I'm saying is that CMM is so tight that in certain cases, the tests actually drive the components to be completely disassembled, which may be necessary. And as a result, operators have to carry excessive stock due to high component removal rate. Plus, there is impact on operator customers. Next slide, please. So component removal rate and maintenance is driven by the following. Boeing 767 maintenance planning data document does not recommend component schedule restorations. So again, components, they all fly to failure. And when components fly to failure, system flies to failure as well, logically. Removals are very random, unpredictable, in other words. Various components can fail sequentially within a short time frame. What I'm saying is that because of the number of components installed in the system, they don't certainly fail at the same time. So every time the next component fails, the aircraft is literally grounded. Numerous components can be replaced in the course of repeat system failure troubleshooting, and which drives unjustified removal rate to about 50%. In most cases, component MRO cannot confirm, but the shop findings indicate that component fault has triggered the flight deck effect. In today's component MRO environment, it's very difficult for maintenance to consider or to determine exactly if their findings were related to flight deck effects. And the problem exacerbates when several components are replaced at the same time. So the difficulty to troubleshoot drives mechanics sometimes to replace 2, 3, 4, or 5 components in the same time. They'll go to the shop, and in certain cases, shop findings may be present on several components, whereas only one actually was the root cause. And that's what I'm saying in the next slide. CMM induction tests may fail all removed components because certain tests have excessively tight limits. The terminology, a little bit of terminology here. Overhaul is defined as repaired is required unless there is developed overhaul. So in this case, if mechanics follow just the CMM, yes, they can specify overhaul, but it will be as good as repaired as required, basically. Component repair scope is inconsistent and may vary from one serial number to another. So basically, if components come in a different condition to the shop, they will also be returned in different conditions. So that varies, that causes the variance in time on wing. So one serial number can last, let's say, 5,000 hours. Another serial number can last 6,000 hours, 7, etc. So there's no consistency in time on wing. And that's where they can't really predict component failures. Next, please. One of the persistent issues in the system is breakage of HPSV and PRVs. HPSV is high pressure shutoff valve, PRV is pressure regulating valve. So wiring failures, they're latent. They cannot be sometimes, since here I'm showing just evident failures when the log is broken off of the circle. But in many cases, the wiring faults, they hidden by the Teflon sleeves that you can see on wiring installed on the terminals. So when wiring fails under the sleeve, sometimes the failures are intermittent and mechanics can't even see that there is a failure of the wiring. So again, it really exacerbates troubleshooting and creates repeat flight deck effects. So here, typical HPSV PRV wiring malfunctions occur due to mechanical failures of lugs installed on studs 1, 2, and 3 of HPSV and PRV terminals block. The fragile design doesn't endure frequent HPSV PRV replacement. Basically, it's like a snowball effect. The more components you replace, the more wiring is susceptible to damage. And it causes incorrect lug crimping and installation, including off-wing engines maintenance. So sometimes even MROs that overhaul engines, they send engines with incorrect wiring, which breaks very shortly after engine is being put in service. So I'm just going to move to the next slide, if you don't mind. So we already went through this slide, but yeah, we've gone through this slide. Sorry, I think I put it twice in the presentation. So can we move on to the next one? So flight deck effect reporting is not consistent. In my vast experience with the system, flight crews don't necessarily report the parameters that maintenance need to be aware of in order to troubleshoot the system. And flight crews may not necessarily be aware of the difficulties of troubleshooting. So um, many flight deck effect reports come inconclusive to maintenance, which really doesn't allow maintenance to narrow down um, troubleshooting failures. So it is essential to report all indication related to and associated with pneumatic system flight deck effects. Um, Even if one element of flight deck effect is not reported, that may cause um, troubleshooting difficulties for maintenance. So I'm listing the the flight deck effect parameters that need to be recorded by the flight crews. Is flight phase, flight level, no PAX takeoff condition, both left and right dock pressure. Uh, Sometimes flight crews don't mention that flight pressure was normal, but maintenance, they need to know if the pressure was normal downstream of PRSOE, because that parameter tells maintenance that the pressure regulation part of the system was actually okay. It worked well. So they can focus on other on other issues like temperature control and indication itself, like wiring. Um, so I'll continue. Both duct pressure, duct pressure fluctuation if present, indication of on bleed air panel, which is the control panel. I've previously shown it on other slides. Um, Also, maintenance need to know the state of engine NTI system. They need to know N1 and 2 parameters, because system is heavily dependent on the system operation is heavily dependent on performance of the engine and engine parameters, and all ICAS messages. Flight crew report is considered complete when the existing flight deck effect combination is reported in its entirety. Like I said before, just one unreported FDE may send maintenance personnel off track. Next, please. So here's a solution process, which is a practical process. It's been implemented before and may be useful to certain operators if they're interested to improve the system. So first of all, wiring needs to be modified. Troubleshooting practices need to be improved. Component bench troubleshooting also is important. So technicians, MRO technicians, component MRO technicians can actually confirm the faults within the components. Another thing is maintenance is component maintenance is very expensive, and there is over 100 alternative parts that can be used, so-called PMA parts, that can be put in all of these bleed system components during component maintenance. Many of these components actually they exceed the reliability of the parts provided by original manufacturers. The work scope for components should be consistent. So if work scope is consistent, time on wing also will be consistent. And based on that, scheduled maintenance program can be accurate and can be improved to add removal intervals for the components to prevent their failures. And certainly FDA reports need to be accurate for troubleshooting purposes. Maintenance programs should not be revised until proper component maintenance has been phased in. Basically, if you revise maintenance program, assuming that the interval is going to be effective and the work scope is not effective, it's going to cost more. It's not going to be a very effective result. So basically, fix the components, make sure that they last certain time, only then make the decision to revise the maintenance program to add removal intervals for intervals for the components. Next slide, please. So troubleshooting, so here's a solution in detail. Troubleshooting procedure effectiveness is in part the function of flight deck effect indication. So I've already gone through it. I'm really reiterating that flight deck effect indication and its reporting is supposed to be correct. If it's not correct, troubleshooting is going to take longer, and aircraft will be grounded for a longer time. So the reports must be properly interpreted. It's not sometimes straightforward how to interpret the flight deck reports. All the flight deck accuracy of flight deck reports, like I said before, it drives accuracy of troubleshooting. What we've also done, we have ranked, actually this is posted on our website, we have ranked all the components based on the most probable causes, which helps maintenance to go to the proper component, because troubleshooting is intricate, and based on historical data of most probable causes, maintenance should be able to actually go straight to the component that has failed most frequently. A troubleshooting sequence should also be adjusted based on probable causes. The current fault isolation manual doesn't account for a component for the probability of failure of the components. Basically, the sequence of troubleshooting does not necessarily represent the most effective workflow for maintenance. So based on most probable cause components, that sequence can be certainly readjusted. Again, we're talking about wiring harness. If wiring is fixed, 25% of the problem would disappear. The tool that Boeing provided for troubleshooting is called Air Supply Byte Module. It's not a very effective troubleshooting tool, because its indication is not necessarily a representative of flight deck effect. So even if there is no flight deck effects, this byte module may show certain faults, making maintenance believe that there is an issue with the system. So there should be other ways, smarter ways to troubleshoot the system. Next slide, please. Can I have next slide, please? Another part of the solution is the collaborative component troubleshooting approach. So I've done it in the past, and it's a very effective method to cooperate for the airlines and MROs to cooperate on finding the confirmed faults within the components. Component MRO mechanics, they don't know the system. And because they don't know the system, it's hard for them to find, to confirm faults within the components. So basically, the objective of the collaborative component troubleshooting is to determine whether the removed component assembly is the root cause of the system failure that caused the removal. Long-term benefits of the process is consistent identification of component assembly confirmed faults, expedient and accurate system and component troubleshooting, collection of component defect data, and establishing trends. So that's an important part in the shops. If piece part data or shop replaceable unit data is not collected, it's hard to build an effective work scope, meaning that interval for preemptive replacement will not be accurate. It allows for proper component failure mode analysis and development, like I said, development of effective component work scopes, which would guarantee failure-free operation for a specified period of time, which is really the definition of reliability. So basically, the operators would get guaranteed time on wing, and guaranteed time on wing guarantees that components can be removed before they fail which is before system failure. Next slide, please. Part of the solution is that holding units, removed units on site before they can be sent to MROs. This process alone can reduce component maintenance costs and assist in system troubleshooting considerably. So the message is that if you remove 3, 4, 5 components, please don't send them to a component MRO right away. Just determine which component actually could be the root cause based on the monitoring of the system within the next, I would say, couple of weeks, approximately. And then you can determine which component actually should be sent to MRO out of all this 3, 4, 5, and it saves a lot of money. And return on investment for establishing this process is very, very quick. We've done it in the past, and it works well. Basically, that describes the process. Next slide, please. So that's the part that I've mentioned before. Scheduled component removals for off-wing restoration substantially reduce system failure rates, but it's premised on development of effective component restoration work scope. Effective work scope ensures consistent restoration quality. And in order to save money and bring consistent restoration in the components, you need to invest. So basically, you have to replace multiple sharp replaceable units, and the cost can be saved if alternative parts or replacement articles, so-called PMA parts, are used in the restoration process. That's also certain CMM tests should be replaced with less invasive testing. As an example, here's a good example. The current HPSO PRV leakage test can be replaced with the already approved thumb check. What is this thumb check? I know it's it's hard to understand what it means, but basically that is it's a check in which mechanics can do in line maintenance to confirm if valve can actually continue in operation. But in the shop environment, that test doesn't exist. So there is a more intrusive test, which actually drives components to be, in the shop, which drives components to be disassembled for unnecessary reasons. Next slide, please. Here is a solution for wiring restoration. If you remember previous slides, modification improvement. If you remember previous slides, the broken wires, the correct wiring harness is on the right, and here's samples of the correctly designed wiring on the right side and the harness that we've used in the past, and it brought a tremendous success to rectify wiring issues. Next slide, please. Our company has developed the flight deck effect reporting mechanism for flight crews. And here is the demo video. I'm not going to play the whole demo video, but if you can play maybe the first minute and the last minute of the video just to demonstrate the effectiveness of the tool, I would really appreciate it.
Boeing 767 pneumatic system is one of the top flight schedule disruption offenders. Its excessive maintenance cost is approximately 50%. Completeness and accuracy of the flight deck effect reporting is fundamental in ensuring accuracy and expediency of the system failure rectification, avoiding shotgun troubleshooting and unnecessary component replacement, with the ultimate goal to reduce operational and maintenance cost. Flight Crew Defect E-Log is an application which allows flight crews or maintenance personnel to report Boeing 767 pneumatic system flight deck effects in real time using mobile devices. The application guarantees completeness and accuracy of flight deck effect reports. It ensures that system fault indication and parameters necessary for system troubleshooting are completed and emailed to maintenance personnel for troubleshooting. The application can be accessed via predictaog.com website by clicking on Flight Crew Defect E-Log button in the top menu. Please review the report. If any corrections are required, please return to the E-Log page and click on the Edit Report
can you
button
go
to
back
unlock
to
existing report for editing. Once the
can you back
existing report has been 767 ATA 36 flight deck.
stop? Can you go back to a minute, let's say, to the third or fourth minute? I just want to show how this app works. It's broken down into sections. Yes, around here. Just play a little bit so people can understand.
767 pneumatic.
Oops. Yeah, so the app is broken down into several sections, which allow to log all necessary information.
Lead air demand by other aircraft systems, such as environmental control and engine anti-ice systems. Please provide flight phase, flight level, and no PAX takeoff condition. Section 3. Please report all ICAS messages observed in flight.
So that's what the flight crews are.
If no ICAS,
you can pause now. Can you go to the last minute now?
flight deck
So the result
will open in a new browser tab. Please review the report. If any corrections are required, please return to the E-Log page and click on the Edit Report button to unlock existing report for editing. Once the existing report has been edited, the Edit Report button will change to the Generate Report button. Please click on the Generate Report button. The edited report will open in a new tab. Please email the generated report to your maintenance organization for review and system troubleshooting. Please note, the generated report can be emailed as many times as required. If you'd like to complete a new report, please click on the Fill Out New Report button. Please note, if you click on the Fill Out New Report button, the report page will reset. This concludes the demonstration of the Flight Crew Defect E-Log functionality. Thank you for your time and attention.
So the entire video is available on our website, and also this application is free to test. It's also on our website. Can you go back to the slides? Yes. So you can access the app. It's a free source. You can always test it. It's under Flight Crew Defect E-Log. So it takes only 3 minutes to complete, but the result is enormous. Once again, I'm going back to the reporting, to the importance of the reporting by flight crews, and that really saves a lot of money just reporting stuff properly. I mean, the indication. Next slide, please. That's it. That concludes the presentation. I hope we're within 30 minutes. If there is no questions, that's it for me.